Okay, so now we're getting into chapter four. The first couple chapters we've been using one language for logic, which was um, propositional logic. And now we're going to be moving into monadic predicate logic, which we've got these sections, but it allows us to do some things that we can't do in propositional logic. So while we are getting into a new language here, the rules of inference and things that we've learned so far are going to apply in the same ways. We just have to get a handle on the actual materials that we'll be using for all of our rules of inference and rules of equivalence, etc. There'll be a couple more rules that come along as well. But while this is going to look completely different at first, it builds on a lot of what we've already been doing, so don't be too intimidated by it. This section, I think, is the easiest to look at and think, I have no idea what's going on. Again, the same with propositional logic, it'll be important to kind of walk through exactly what something means, and then that'll make it sort of more intuitively available to you, where it's easy to just sort of wash out and lose a sense of what you're looking at if you don't just take it one step at a time. So again, important here to go really slowly and make sure you understand everything, even though it's going to be difficult to grasp some of it, and it'll look real easy to just skip when you're doing your reading. But it's important to make sure that you get one step before you move on to the next. So here we have an example of why predicate logic is useful in ways that propositional logic is not. So if I say Sydney is reading, and then therefore someone is reading. In propositional logic, we would just say S for Sydney is reading, and maybe R for someone is reading. So in that case, we just have two different statements that aren't intuitively related to each other. There's nothing that captures the relation between Sydney reading and someone is reading. So propositional logic captures logical relations only among propositions. So for arguments like this one, where Sydney is reading, therefore someone is reading, we need a logic that captures logic relations inside propositions. So this is something that predicate logic does, where we look not only just at propositions, but on properties that things have. All right. So a predicate logic builds on propositional logic by introducing quantifiers and by dividing propositions into singular terms and predicates. So we'll have a singular term, and we'll be able to attach predicates to it. And we'll have, when we consistently use a singular term, we'll be able to attach different predicates to it and say that different predicates apply in other cases. But in order to do that, we need this new language that we're going to be getting here. So dividing propositions into singular terms and predicate allows us to capture logical relations within propositions, where it's not just when we say Sydney is reading, we're not just saying S, we're not reducing the entire proposition to just one variable, but we're able to capture different aspects of that proposition and make those explicit. So introducing quantifiers allow us to express quantities like someone, something, nothing, and everything, and related terms. So this, if it's not exactly clear what a quantifier is yet, where if we want to say, well, everything is red, or nothing is blue, or some things are green, quantifiers allow us to express this relation without just reducing it to a single proposition. So as with propositional logic, we begin by specifying a formal object language. So we're going to call this, it's confusing because propositional logic and predicate logic both seem like they'd be PL. There's other predicate logic languages or different further levels of predicate logic languages in the book that we're not going to cover in this course, but if you're interested in, there's other logic courses at UGA that go into polyadic predicate logic, but here we're just doing monadic predicate logic. So because we're doing monadic predicate logic, we're going to call it M. So the vocabulary of M includes lowercase letters and uppercase letters. So before in propositional logic, we just had uppercase letters, but now we have both lowercase and uppercase letters, and they'll allow us to express a certain relationship that we wouldn't be able to in propositional logic. We'll use the same 5 propositional operators that we had before, the tilde, the dot, the vel, the horseshoe, and the triple bar, for the negation, the conditional, the disjunction, the negation, the conjunction, the disjunction, the conditional, and the biconditional, and then 2 quantifier symbols. So one of these is going to look like a backwards E. That's going to be the existential quantifier. That means that for at least one thing, something is true. So something is true of something. And the universal quantifier, which looks like an upside down A, which is going to say for all things, for everything, something is true. And of course, punctuation marks in the same way that we used them before. So in all predicate logic, we represent particular things using lowercase letters that we call singular terms. So there's 2 different kinds of lowercase letters. This is really important. So A, B, C, let's say the first couple letters of the alphabet are going to be used for what we call constants. The last few letters of the alphabet, in the book, they're using V, W, X, Y, and Z, but for our purposes, we're pretty much just going to be using X for variables. And I'll go into the difference between constants and variables more in the future, but basically a constant is a specific particular thing, whereas a variable stands for something kind of in general. And now it can mean a specific particular thing, but it doesn't specify it with any sort of precision. It just means something. And that'll make more sense later, I hope. I'll explain that in further slides, but that's sort of a preview. There is an important difference between constants and variables. Constants, we're going to use the first several letters of the alphabet here, A, B, C up to U. Anything up to U we'll treat as a constant. V, W, X, Y, and Z are going to be variables. So singular terms are always connected with predicates. So predicates are going to be represented by an uppercase letter that precedes a singular term, and this stands for some property. So we can translate Sydney reads as capital R, lowercase s, with the R and S right next to each other. So Sydney, as a particular thing in this case, is going to be represented by S, and the capital R is going to represent a property that Sydney has, or a predicate that we could attribute to Sydney, which is that she reads. All right. So a predicate of M followed by a constant is called a closed sentence and expresses a proposition. So if we have something like John plays the piano, we could represent this as PJ, where the lowercase j stands for John. Now I'm going to emphasize this because this can be a little bit confusing. A lot of the specific terms that we use constants to represent are going to be things like proper nouns. So intuitively, it's a little bit confusing to represent John as a lowercase j and this property that John has with a capital P in front of it. But that's just the way it is here. I'm flagging it here so that you can keep that in mind. It's an easy mistake to make where we want to substitute a person's name for the capital letter in predicate logic, but the capital letters only stand for properties that the constant or the singular term has. So John plays the piano is one example. Anne is tall is another example. We represent Anne with a lowercase a. Lowercase a stands for Anne, and the capital T stands for the property tallness. Anne possesses the property of being tall. The bed is white here in this case. The lowercase b stands for the bed. White is the capital W. So this thing, B, or the bed, has the property of being W, white. Okay. Gabe looks tired. we could represent in this way, where the lowercase g stands for Gabe, and looking tired is the property T. So we could say TG here, which stands for there is a thing, G, which we know is Gabe, that has the property T, or looks tired. So we call M monadic because the predicates take exactly one singular term. Here in when we're doing monadic predicate logic, there's only going to be one singular term that predicates apply to. That will keep things simple. Like I said, there's other courses that you can take that get into more advanced symbolic logic, where you end up doing polyadic predicate logic, where there's more than one term that's being used. But for our purposes in this class, we just have to worry about the one singular term. So a predicate followed by a variable is called an open sentence. So an open sentence is going to be kind of like an incomplete sentence, where something is missing some material that we would have to fill in order for it to be a complete sentence. So if we have the expression px here, x is not going to stand for any specific concrete thing in the way that the previous examples with the constants did, because x is a variable. It just means X plays piano. There is a thing, X, that plays the piano. Now, we don't know what it is. We haven't specified what X is, but we have specified that there is just something that plays piano. Z is tall. Again, the property tallness here is being ascribed to something, but we're not specific about what the something is in that case. And Y is white, which you can see Y here is just another variable, stands for something, but it has the property of being white. And V looks tired. So again, these are all just different constants. In this course, we're pretty much going to be using X as our standard constant. In all the homework assignments, I'll use X as the standard constant. Sorry, X as a standard variable. Very important. X is a variable, not a constant. So I'll use X as a standard variable. But Z, Y, V, these will be variables as well. So by themselves, open sentences do not express complete propositions. To turn them into a complete proposition, we need quantifiers. So quantifiers are operators that work with variables to stand for terms like something, everything, nothing, and anything. So when we just say, for example, is tired. Well, we could say specifically something is tired. We could say Sydney is tired, or Gabe is tired, or whoever it was. So we can say that this specific, in this case, this thing is tired, or this person, and we would use a constant to represent any specific object like that. But if we want to say something like something is tired, or everything is tired, or nothing is tired, then we're not specifying a specific thing. So we could use an open sentence like px to express that proposition, but we'll need the quantifier to get something or everything or nothing. We wouldn't want to represent something, anything, or nothing by using a singular concrete term, because these are broader than that and have a meaning that's beyond those. So we use two symbols for these quantifiers. The existential quantifier is represented by this backwards E symbol together with a variable. So for example, you would see this existential quantifier where it's going to have this backwards E and then an X, and then that'll mean for at least one X, something is the case. The universal quantifier is represented by the symbol with this upside down A together with a variable. In this case, it's here with a Y, so it would be for all Y's, for every Y, something is the case. So the existential quantifier is used for there exists at least one. This could also be translated as something. There is at least one thing that has this property. So this first formula here, where we can see the existential quantifier in front of the px, we could read this as for at least one x, or the way it's written here is there exists an x such that x is p, or something is P. There is at least one X that has the property P. The universal quantifier is used for all, every, or for any. So here we have the universal quantifier in front of Px, and this is going to mean for any x, x is P, or everything is P. For all x's, the property P applies, or all x's will have the property P. So here's some examples. If I want to say everything is great, I could represent that in this way. For all x's, x has the property of being great. So just for everything, everything has the property of being great. Now this is an important point to make because this is an easy mistake to make. When I say everything is great, and these quantifiers work just like our other operators, where in the example everything is great, the major operator here is going to be the universal quantifier. And in the next example, when we have nothing is great, this could be represented in two ways. In the first way, we're using a universally quantified formula, where the major operator is the universal quantifier. And in the second way, we have an existentially quantified formula, where the major operator is the negation. Now you can tell which one is which because the negation will be kind of on the inside of the universal quantifier. So the universal quantifier being on the outside is the major operator in that case. And in the second case, the existential quantifier itself is what's being negated. The negation is not inside the existential quantifier, so the negation is the major operator in that case. Now, when we think of, well, what is the opposite? What does it mean for everything is great to be negated? Well, nothing is great is not the negation of everything is great, as you can see here. The negation of everything is great would have the negation as the major operator on the outside of the formula that we have in the first case for everything is great, where it would be it's not the case that for all x's, g is the case. Now, nothing is great is not the opposite of everything is great, because the opposite of everything is great is there is at least one thing that is not great. Nothing is great can be expressed either in a universal way, where I say for all x's, it is not the case that gx, or for everything, anything that we take, it is not the case that it is great. Or, and the second way of expressing it is not the case that there is at least one thing that is great. If I want to say nothing is great, I can express this with an existential quantifier by negating the existential quantifier, and to say it is not the case that there is at least one thing that is great, which would imply that nothing is great. If it's impossible for there to be even one thing that has the property of being great, then this is the same as to say that nothing is great. Now, if I want to say something is great, I could just express that with the existential quantifier and then gx. And this would read, for at least one x, there's an x with the property g. So for at least one thing, it is great. If I want to say something is not great, I could say there is at least one thing that does not have the property g. Or I could express this as, it is not the case that for all things, the property g, great, applies. So these are sort of two different ways of expressing the term something is not great. And again, you can see this is kind of the inverse of nothing is great here, where in one case we're using the existential quantifier as the major operator, in the other case we're using the negation of a universal quantifier as the major operator. And if you think about what these mean, you can understand that both of these are just different ways of expressing there is a thing that is not great. In the first case, with the existential quantifier, there is at least one thing that does not have the property of being great, so something is not great. And with the universal quantifier, we could say it's not the case that everything has the property of being great. So either everything has the property of being great, or at least something doesn't have the property of being great. If it's not the case that everything has the property of being great, that's because something would be lacking that property. which is to say something is not great. Notice that the two statements with quantifiers and negations can be translated in two different ways. So everything lacks a property, or it is not the case that something has a property. So some of these sentences we could use either the universal or the existential quantifier to express them, as you can see here. So most English sentences are best translated using at least two predicates. The subject of a sentence is what is discussed, and the attribute or grammatical predicate of a sentence is what is said about the subject. And both may contain multiple logical predicates. So in the sentence, lizards are reptiles, the subject is lizards, and the attribute is that they are reptiles. So this is best represented using one predicate for the subject and another for the attribute. So in this case, we'll use first the universal quantifier, and then we'll express the relation here. So we can read this like, for all x's, if x has the property L, then x has the property R. Which means for everything, if that thing is a lizard, then it is a reptile. If x has the property of being a lizard, then x has the property of being a reptile. And this applies to all cases. Now because this is a conditional statement, it is not saying that everything is a lizard. It is just saying that if something is a lizard, then it is also a reptile. All right, universally quantified propositions tend to use conditionals between the subject and the attribute, like in lizards and reptiles. So if it is a lizard, then it is a reptile. If we can take any example, if it is a lizard, then it is a reptile. If it's not a lizard, then we don't have to worry about it. Maybe it's a reptile, maybe it isn't, but that's not what we're trying to express here. So existentially quantified propositions tend to use conjunctions between the subject and the attribute. So we can see in this case, there is at least one x such that x is a lizard and is brown. Something is both a lizard and brown. Now this doesn't apply to every lizard, but it just says that of the things that exist, at least one of those things has two properties at the same time. In the first case being a lizard, and in the second case being brown. So for at least one x, x has L and x has B, where L is being a lizard and B is being brown. And that'll be expressed in this way. Just very careful not to mix these up. As kind of a rule of thumb, you can think about existentials involving conjunctions, whereas universals will translate as conditionals, but you'll have to use your judgment again with these translations. Translating normal English sentences into a symbolic logical form, there's some nuance to it and some things aren't completely clear, and there's not strict rules to apply. So you'll have to think about what the meanings of the sentences are. So using the same example, the phrase, there is at least one x such that if x was a lizard, then x is brown, would say there are some things such that if they are lizards, then they are brown. So this is sort of a weaker claim than the original one, which is to say that there is at least one thing that is both a lizard and is brown. It's asserting that there are two properties that exist simultaneously in a thing, where this is saying that if there was such a thing L as a lizard, it's also possible that it would have the property B. So this is a little bit of a weaker claim. And the proposition for all things x, Lx, and Rx would be to say that everything is both a lizard and a reptile. For all things, these two properties are the case, being a lizard and being a reptile. It's pretty clear, I think, to most of us that that's not the case. So lots of things that you can think of that are not lizards or reptiles. A pencil, for example. All right, so many sentences have complex subjects and or attributes, so these are translated with multiple predicates. So all glass tables are breakable, we could express in this way. For all x's, if x is glass and x is a table, then it has the property of being breakable. So if we want to say all glass tables are breakable, we're saying that, okay, everything that is both glass and a table that counts as a glass table has this property of being breakable. So we know if it is glass and it's a table, then on the other hand, it is breakable. So we could express it like this. For all x's, gx and tx, if gx and tx, then bx. Some glass tables are expensive. So this is just asserting the existence of some thing that has a set of properties together. So we'll express this as an existentially quantified formula with a couple of conjunctions. So we could read this formula here as there is at least one x such that x has the property of being glass and being a table and being expensive. Some glass tables are expensive, so there is at least one thing that has all three of these properties of being glass and a table and expensive at the same time. Ice cream is cold and delicious. So this is a pretty strong claim where it's just ice cream in general. So we're going to use a universal quantifier for this. For all x's, if x is ice cream, then it is cold and delicious. Because the way this English sentence is phrased, while we might think of this normally as being something like a subjective opinion that doesn't hold any sort of universality and necessity that we're expressing here in the logical form, when we're translating something into its logical form, we need to take seriously the statements that are being made. And if we want to say that something is more like a subjective opinion that isn't going to have the necessity of universal law, then we should have said it differently in the first place. So if we're going to translate a sentence like ice cream is cold and delicious, we need to take literally what it's saying, that there is a thing, ice cream, that will always have these properties. So we can say for all x's, for anything, if that thing is ice cream, then it will have the properties of being cold and being delicious. Because if it's ice cream, it will have those properties that just always comes with being ice cream. So for all x's, if ix, then cx and dx. So here, all cars are new or used. So we're using all here, so it's pretty clear that we're going to need a universal quantifier. So we could express this as such. For all x's, if x is a car, then it is either new or used. For all x's, if cx, then nx or ux. So of all the objects, if it is a car, then there are two possibilities. It can be new or it can be used. All right, so something is in the water, and someone is in the water. Both sentences are quantified existentially, but the scope of the second claim is narrower, since it rules out all things that are not people. This is pretty clear. Something is in the water could apply to anything, whereas someone in the water is talking about just a subset of the things that exist. So to show this, we add a predicate for personhood, such as px. So if I want to say something is in the water, I can say there is at least one thing x such that wx. There is at least one x that is in the water. In this case, the capital W will stand for in the water. If I want to say someone is in the water, I could say there is at least one x such that x is a person, px, and x is in the water, wx. There, of all the things that exist, there is at least one thing that has the properties of being a person and being in the water, which is to say, someone is in the water. Other types of propositions requiring a predicate for personhood include everyone, anyone, or no one. So this is just something that we add into our, if we're being specific about the type of object that we're discussing, then we would go ahead and add that into the formula. So anyone who has been to Berlin has seen the Brandenburg Gate, is our example here. So we could express this as such. For all x's, if x is a person, if x is part of anyone, and X has been to Berlin, then X has seen the Brandenburg Gate. So because we're using anyone, which is not just anything, but because we're talking about people specifically, that will be one of the predicates that we use when we're specifying the conditions for the necessity of having seen Brandenburg Gate, which will be for all x's, px and bx, if px and bx, if you're both a person and have been to Berlin, then it is the case that this object, this person, has seen the Brandenburg Gate. Everyone who visits Antwerp returns. So we could express this as follows. For all x's, if x is a person and visits Antwerp, then x returns. So P here would be is a person, A stands for visits Antwerp, and R stands for returns. These are all different properties that an object could have, that a thing could have. And so we're saying that for everything, if it has these two properties, being a person and visiting Antwerp, then it will also have this third property of returning. So no one in Liechtenstein visits Nantes. So there's two different ways we could express this. In the first case, it's for all x's, if x is a person and x visits Liechtenstein, then it is not the case that x visits Nantes. So we could express this in a universally quantified ways, which is for all objects, if these two properties are true, that x is a person and x visits Liechtenstein, or that it is in Liechtenstein, then it is not the case that they visit Nantes. Or I could say, it is not the case that there is at least one thing that has these three properties. Px being a person, and being in Liechtenstein, and visiting Nantes. There's nothing in the totality of objects that has all three of these properties. So I could express that with the existential quantifier there. It is not the case that there is at least one x, px, and lx, and nx. So only is a little bit tricky, just as it was before. So only usually indicates a universal quantifier. It is usually equivalent to an all proposition with antecedent and consequent inverted. So if I say only members are allowed in, now again, you have to remember the relationship between only statements and antecedents and consequence, as opposed to if X then Y type statements with antecedents and consequence. So if I say if P then Q, then what follows if, in this case, will be an antecedent, and what follows then will be the consequent. But if I say only if P then Q, then the order is going to be flipped. So the same thing will apply here. When I say only members are allowed in, I would translate that in this way. For all x's, if x is allowed in, then x is a member. Because the sentence is saying that the only people that are allowed in, or the only things that are allowed in are members. I know that if something is allowed in, then it is a member. It's possible that something could be a member and not be allowed in, so it wouldn't work the other way around. But I know that if something is allowed in, then it has to meet this condition of being a member, because members are the only group of things that are allowed in. So for all x's, if x is allowed in, then x is a member. So I could also say all who are allowed in are members. This expresses the same thing. For all x's, if x is allowed in, then x is a member. And this sentence is sort of a little bit easier, I think, to intuitively grasp how to translate in this way with a conditional, but it's really just expressing the same thing as the first sentence. So if the grammatical subject of an only sentence has two predicates, we need to think a little bit about how we regiment it. So in the example here, only long operas are boring. we could represent this with this formula, which is that for all x's, with the universal quantifier, for all x's, if x is boring, then it is the case that x is long and is an opera. Now, technically, there isn't anything wrong with this. Only long operas are boring could mean that for everything, if it is boring, then it is long and an opera, where it's saying that the only things that have the property of being boring are long and operas. So that if we know that something is boring, then we know that it's long and an opera, because being long and an opera are the only things that allow something to be boring. However, that's probably not what is meant here. It would be better to regiment this in a different way. So instead, we'll invert the two attributes long and boring, leaving the main subject operas alone. So we could also regiment this like such. For all x's, if x is an opera and x is boring, then x is long. So instead of reading the sentence, all long operas are boring, or sorry, only long operas are boring, and reading it as limiting the conditions under which an object can be boring, if we consider it to be an explanation of what types of operas are boring, where we're talking about what types of operas are boring rather than what types of things in general are boring, and we want to say that, well, only the long operas are the boring ones. That's probably more accurate than to say the only boring things are long and operas. Instead, we're going to say the only boring operas are the ones that are long. So we would express this like so. For all x's, if x is an opera and x is boring, then x is long. Or for all x's, ox and if ox and bx, then lx. So the main quantifier of most of the previous quantified propositions, such as for all x's, ox, and if ox and bx, then lx, has been the quantifier. However, many propositions contain multiple quantifiers. So we can also have expressions like this, where we say for all x's, if x is an opera, then there is at least one x such that px. Well, I guess I should say for all x's, ox. We don't know if it's opera that we're talking about here exactly. But in this case, the main operator would be the horseshoe, the conditional statement. Here, the main opera is going to be, or the main operator, I keep saying opera. I've got it stuck in my head now. The main operator is going to be a conditional. Now, if you see, we have some parentheses around the entire thing, and then a negation, not a conditional. The main operator here is going to be a negation. So we have the parentheses around the entire thing, and then a negation in front of that. So we want to say it's not the case that if for all x's, ox, and bx, then there is at least one x, ax. We want to say that this relationship doesn't hold, so we negate the entire thing. All right. Here, the main operator is going to be a conjunction. We're going to say there is at least one x dx, and for all x's, if x is k, then x is s as well. In this case, it's a disjunction. There is at least one x sx, and there is at least one x sx, or for all x's, if kx, then sx. So nouns modified by adjectives are often best regimented using a conjunction of two predicates. So we'll see an example here. If we want to say glass table, we'll say there is something that has two properties at once. G being glass and 2 being a table. So a glass table will be defined by having these two properties of being glass and being a table. So we could express that as a conjunction of these two terms. We could say a boring opera in the same way. If X is a boring opera, then X has the property of being boring, and X is an opera. However, many context-sensitive adjectives cannot be regimented in this way. So, for example, a jumbo shrimp is not something that conjoins the quality of being a jumbo with the quality of being a shrimp. It's jumbo for a shrimp. It's, relatively speaking, jumbo-sized. So therefore, it is better regimented with a single predicate, where we would think of it, we would just say X in this case for jumbo shrimp. Because, yeah, if we just applied the predicate of being jumbo, well, that's going to mean something in different, it's going to mean a different thing in different cases. A jumbo elephant is going to be different from a jumbo shrimp. Whereas glass as a material is going to be glass even if its different colors are used in different ways. It still has the property of being glass. That it's not relative in the way that being jumbo is. So, a little bit of a recap on this. The vocabulary of monadic predicate logic includes capital letters A through Z used as one-place predicates. These capital letters stand for a property that something has. Lowercase letters used as singular terms. So A through U going to be used as constants. And we're mostly going to stick to like A, B, C, D. We shouldn't have too much stuff that goes beyond that. So A, B, C, D will be used as constants, which will be when there is a specific given thing that has some property. And V, W, X, Y, Z will be used as variables when there isn't a specific thing that has the property. We're just talking about properties in a more open way. We're saying maybe there is at least one thing that has a property, or for all things, if it has this property, then it has this other property. And for variables, we're pretty much just going to use X as our standard variable. We have our 5 propositional operators: the negation, the conjunction, the disjunction, the conditional, and the biconditional. These will be the same as before. You should be familiar with these by this point. And the 2 quantifier symbols, which are new. This backwards E thing is the existential quantifier, which stands for there is at least one thing or something has some property. And this upside down A, which is going to stand for all things or everything. And then, of course, the punctuation with parentheses to make sure that we're continuing to use things are going to continue to be well-formed formulas. All right. So the next thing to go over is the operator and quantifier scope. To understand formation rules and quantifiers, one has to understand their scope. The scope of an operator is its range of application. And the scope of a quantifier is whatever formula immediately follows the quantifier. So, for example, if we have this formula for all x's, dx and px, which we could read as there exists something that is d and is p, the quantifier scope is dx. Sorry, I messed this up. Let me redo this. This is how easy it is to make a mistake here. So there, the formula reads, there is one thing dx that is itself one well-formed formula on its own, and we're going to say px, or x is p. So there exists something that is d, and x is p. The quantifier scope here is dx. The quantifier is only modifying dx. It is not modifying px. If it was going to modify the entire thing, we would need parentheses around the dx and px for the existential quantifier to modify the entire thing in this example here. So here, this sentence says there is at least one x such that dx and px. There exists something that is both d and p. So the quantifier scope here is everything that follows it in parentheses, dx and px. There's no parentheses in the first case, so we have 2 different things that are part of that conjunction, where here the conjunction is inside the scope of the existential quantifier. So if what follows the quantifier is a bracket or parentheses, then any formulas that occur until that bracket is closed are in the scope of the quantifier. If what follows the quantifier is a tilde, then the tilde and every formula in its scope is in the scope of the quantifier. So everything that the tilde applies to, if the tilde is what's immediately after the quantifier, that will all be inside the scope of the quantifier. The quantifier will be quantifying everything underneath that. So if what follows the quantifier is another quantifier, then the inside quantifier and every formula in the scope of the inside quantifier is in the scope of the outside quantifier. So we can think of these applying in a similar way as tildes apply, where they're just stuck on the outside of something in the way that we would negate a formula. The negation of a formula negates everything in the parentheses that follows it, or it just negates the thing that it immediately follows if there's no parentheses there. So quantifier to scope determines which variables are bound and which are free, if any. So quantifiers bind every instance of their variable and their scope. So we can see here that Sx is outside the scope of the existential quantifier. So that's not an existentially quantified variable. So we have, there is at least one thing, there is at least one x, dx and px, or Sx. So the first two variables are bound, dx and px applies to the same thing, whereas Sx is just an open x is S. So the third is free, since it's not inside the scope here. But if we add some parentheses, such that the parentheses that immediately follow the existential quantifier enclose everything that is around it, then all three variables are bound. There is at least one x such that either x has the properties of being d and p, or it has the properties of being s. So a well-formed formula that contains a free variable is an open sentence. So here, even though part of the sentence is or one of the subformulas in this well-formed formula is closed, the first disjunct, which says there's at least one x, dx, and sx, because the major operator here is the disjunction, and because part of the one of the disjuncts is an open sentence, in this case sx, then the entire thing is going to be an open sentence. A well-formed formula that contains no free variables is a closed sentence. So here, because everything is under the scope of this quantifier, it's a closed sentence. There's no free variables in play. So translations from English into M should ordinarily give us closed sentences. If you think about what an open sentence is, where we're just saying X is S, or we're sort of just saying like is red by itself without something that predicate applies to. Is tall doesn't really mean anything to us. So if it's going to make sense in English in the first place, then we should be able to get a closed sentence out of it. So here's some formation rules. A predicate, capital letter, followed by a singular term is a well-formed formula. So for any variable beta, if alpha is a well-formed formula that does not contain either there is at least one alpha, or for all alphas beta, then there is at least one beta alpha, and for all betas alpha are well-formed formulas. So let's think about this for a second. This is really just saying that when we have a quantifier, and we're going to use a variable with it, pretty much always x in this case, but we're using the Greek letters here to understand that it could be anything. Then something that follows that isn't itself going to be using another quantifier is a well-formed formula. So if alpha is a well-formed formula, so is not alpha. This is something that we're already used to. If alpha and beta are well-formed formulas, then so are all these combinations, alpha and beta, alpha or beta, if alpha then beta, and alpha if and only if beta. Again, these are repeats of what we had before, and these are the only ways to make well-formed formulas. So we're essentially just inserting the quantifiers as another way to make well-formed formulas, and the rules for a quantifier are going to be quite similar to the way a negation works in a well-formed formula. Right, so an atomic formula of n is formed by a single use of rule 1, a predicate followed by a singular term. So this might be a little bit weird because the smallest unit here is going to have two terms in it, as opposed to just one that we had in propositional logic. A single capital letter was the atomic formula. But here in atomic formula, the smallest unit that we're going to have is going to be one predicate with either a constant or a variable. So PS is something S has the property P. KX, since we're using a variable with X, it's just going to be is K. LB is there is something B that has the property L. MT is there is something M that has the property T. And Z again is going to be a variable, so it just is A. Complex formula in monadic predicate logic is a well-formed formula formed in any way besides a single use of rule 1. So complex formula, if we have anything more than just these atomic formulas, it'll be complex. So a subformula is a formula that is part of another formula. So if we take this first example, there is at least one x such that dx and px or sx, we can see that there is a couple of formulas inside the quantifier here. So dx, px, and sx are each the individual atomic formulas that are the smallest parts. Dx and px is a conjunction that makes the next formula outside of those atomic formulas, and then outside of those parentheses, we're going to get the disjunction between dx and px and sx.